want to just do a sort of a short overview or sort of a short discussion of what we mean by filters and just some of the terms we use when we try to describe these filters. And typically when we talk about filters, there are three filters we'd like to have: a low pass, a high pass, and a bandpass filter. In a low pass, where I want to be able to have basically in a very tight window with sort of a fixed gain for that output. For a high pass, I'd like to be able to have the same sort of thing but at higher frequencies. And a bandpass, I'd like to have it sort of in the middle where things are blocked elsewhere. Now, I really wish I could find a perfect filter. I wish I could find a filter that basically just gave me everything perfect right along that line and then just dropped to zero and everything was great. You can't build those. And what's even harder is that there's usually a range where, you know, I have some sort of signal here. There's going to be some variation on the transfer function to try to often get a good response. And then at the lower end here, there's at least sort of a minimum sort of stop band gain. Usually it's going to be right at this point is going to be the critical question. But you never know depending on the filter that you're building. And so these things are going to be important. And so what we have to do is define a range of questions, one of which is, here is the passband, here is the bandwidth for a low pass filter where the signal should go through. It's kind of intuitively what you'd expect in frequency for a filter. This is where things should work. There's a stop band where things should basically be attenuated. They should be at least below this stop band gain. They can be below it. That would be great. And there's a place where the passband bandwidth will sort of encompass. That's usually a parameter. It's specified in a couple different ways depending on who wants to talk about it. The key is to recognize what the concept is, and you can always pick it up. So I need to have some passband gain. I need to have that the passband gain is within some variation. We're going to call it epsilon. That's a pretty typical parameter used. That I need to keep it within some amount. I could specify that in percentage. I could talk about it in a certain amount of dB, which is effectively percentage. So either way, I can guess this kind of concept that would kind of work out well. And then I have a stop band frequency because this is where the stop band. Now you'd like to say, well, isn't that right where the passband is? And the answer is not exactly, because I need to absolutely I need to have some region here for this to drop down to that point. I wish I had a perfect filter, but that's hard to do. By the way, because there needs to be some range here, and the tighter the range, the harder the filter typically is to build. Okay, the higher the order, the more expensive it is. Understand that's really important, because if I'm not careful here, that gets fairly costly. Now, if you're saying, oh yeah, for example, I take Nyquist and I sample something twice that amount and I just filter it, I'm good to go. Here's the problem. I can still do a low-pass filter or some filtering operation afterwards. That filter is not going to be a brick wall filter. It's not going to be a perfect drop. And so that nice sort of factor of 2 for Nyquist is not what you're going to be seeing in a typical situation. It's going to have to be higher than that in practice. But these are the key things that you're going to look at in all of these cases. In the stop band, and there shouldn't be anything here. The high-pass filter is exactly the flip of this, exactly the reverse, where I'm going to be saying, okay, here's where I want a passband gain to be relatively constant over the region I care about. This probably doesn't go to infinity, because no circuit goes to infinity, but close enough in these kind of cases. There's a stop band gain at the low end, and then you have your stop band and passband frequencies. So it's basically the reverse of it. In fact, you can almost argue that between here and here looks like this is an S, or in frequency, this kind of looks like it's 1 over S. Which is a pretty good way to argue and kind of transform anything that's a low-pass filter to a high-pass filter. Now, bandpass filter gets a little more interesting because that means I have a region in the middle that I care about. There's usually a center frequency I'm going to work with. There's usually some spread of the passband I have to look at, and now I'm going to have 2 different corners, and I'm going to specify it in different ways. Either I'll specify both frequencies, or I'll specify what's this FC and what's the percentage of that I'm looking at from my passband. Could do that in a couple different ways. But I'll also have stop bands, stop band gains. They don't have to be the same, although often they are. And then 2 stop band frequencies, because again, I need these separations, plus an epsilon in the passband. And so this is a typical way that you get it. In this particular case, of course, this means I have multiple parameters that I have to use to make sense of the system. But in all of these cases, this allows me to get a very nice frequency response. And a nice way to say, here's what my filters look like, and therefore I create a frequency response, and therefore from that transfer function, I then say, oh, now how do I then implement such a filter? So this is the usual flow and approach that you would imagine in these cases.